Welcome to Sigma Solver, guys. Before I start the video, I want you guys to smash the like button. This helps the YouTube algorithm and keeps me motivated. And if you are new here, then subscribe to my channel and press the bell icon so that you never miss an update. So without any further ado, let's get started. So today we are going to look at a different topic, which is Digital Difference Analyzer, and this is quite popular with the computer graphics paradigm of problems. So we'll see that. Let us read the question first. Explain the Digital Difference Analyzer method for generating line segment between two given points. Write down the procedure in algorithmic form and hence generate a line segment from 2,3 to 8,7. The question is pretty simple. So we'll dive in with understanding what is DDA specifically. So as introduction, DDA is Digital Differential Analyzer and is one of the most fundamental line generation algorithms used in computer graphics, right? So one thing which we can recall is when we draw a line on paper, we have a smooth stroke, correct? But for computers, displaying images is via pixels, right? And those pixels end up on a raster screen. If you want to know more about raster screens, I'll basically put a video link in the I button here. You can check that out. And since these pixels are discrete, we can't directly draw a continuous line, right? We need an algorithm to select the best fit pixels that approximate the desired line. We already know by basic fundamentals is there are analog signals and digital signals, right? So when we are drawing a line on paper, it is analog signal, right? So smooth curve is possible like this, but in computer it is like 0 1 0 1 like that, right? It can't be in the middle of it, right? So that is the problem with drawing a smooth curve, and we can see that we are using best fit pixels instead of just drawing it out. Okay. DDA algorithm solves this problem by using incremental calculations to determine the intermediate points, as I said, between two given endpoints of that line, right? So every line is broke into two mini segments, right? And those segments and their points consisting are basically calculated via incremental method. Where is DDA used, right? So what are its applications? So DDA is used in computer graphics, as we are going to see, drawing lines, polygons and outlines for shapes. CAD, computer aided design, rendering and wireframes and edges. This is quite popular. Game development, drawing 2D objects efficiently. Image processing, approximating geometric shapes. Like there are many others, but most importantly, in the industry, these four are kind of trending. Then we come to the problem itself. So we want to draw a line segment between 2 points x1 y1 and x2 y2. The challenge, however, is we can't plot a fractional pixel like 2.8 and 3,7, right? We must find the nearest integer pixel coordinates. We'll see how. The algorithm should be fast and simple, avoiding floating point multiplication wherever possible. Because now we see that we got these two, and via formulas we know that there will be multiplication involved. So we have to find a method to avoid those multiplications, right? Because we already know that in computer a multiplication is nothing but repeated additions, right? So we need to lessen that in order to draw the particular given line more fast. The idea of DDA. So first we compute the slope of the line, the traditional method, right? We've seen this many times. Depending on the slope, if m, that is the slope itself, if m is less than 1, then increment x by 1, okay, and calculate the next y. Okay. But if it is greater than 1, then increment y by 1 and calculate the next x. It is quite simple, right? If we look at it from this particular angle, let's say the first quadrant itself, in these region, let me change the pen. In these regions, we see that x is traveling faster, right, in respect to y. Okay. So we know that if we increment by 1, then whatever we calculate with y, it will be more accurate. Similarly goes for the next part. So this is kind of the intuition behind. This way all the intermediate points are generated. This same logic what I just told can be applied across multiple quadrants and extended across. Then we come to the DDA algorithm, the step by step which was asked in the question. So first input, which is the two given points x1 y1 and x2 y2. We calculate the dx, right, the difference x2 minus x1 and y2 minus y1. Then we find the number of steps required. So it is max of modulus, which is the absolute value of dx and dy, right. Both of them we are taking the absolute value and then checking the maximum out of it. Then we compute the increments. So for x increment it would be dx upon steps, and for y increment it would be dy upon steps. So then we start from x1 y1 and iterate step times, right. So this is a particular number, how many times we need to iterate this. So we plot the pixel at round x and round y, because we know that we cannot plot fractional pixels. We update this and the cycle repeats itself basically, right. Now as you can see that this is a plus sign indicating that y and x increment can be either positive or negative, right. There is no absolute marking here indicating the same. Okay, now we will go to the actual problem which we have. So the line from 2 comma 3 to 8 comma 7, we initialize it with x1 equal 2, y1 equal 3, x2 equal 8 and y2 equal 7. We calculate dx and dy. We see that the maximum out of this is 6, so it is dx. So we compute the increments, which is dx upon steps, so 6 by 6, which is 1. Then we calculate y increment, dy upon steps, which is 4 upon 6, which is nearly equal to 0.67, right. Then we calculate the points, okay, according to what we need to plot. So that would be a table. So here we will see step 0, we got the initial point, and since we are going to see all the calculations and then round them off here, so I am just putting 2 decimal place, 2.00, 3.00, the plotted pixel is the same. For the first one we increment it by 1 and this by 0.67, right, and then we get the round off as 3,4. Similarly for this one, plus 1 and plus 0.67, which is 4,4, okay. Then it is 1 again with 0.67 we get here, and so on, right. We continue up till the number of steps that is required, which is 6. Once this is done, then we can plot the pixels in any grid. I have not drawn the grid here, but I think the idea is clear. So we can plot that. Next is the inference. Now one thing I'll just will mention here is the grid size doesn't matter, okay. Whichever grid size you can follow for your graph which you might need to create, but the idea is these points are only going to be present there. Mark the labels accordingly and that's it. Then we come to the inference. So the DDA algorithm is easy to implement and works for all slopes as we just saw. However, it uses floating point operations, okay, which is the rounding off for increments, right. First we calculate the fractions and then we particularly round them off. So this type of approach is generally slower as compared to Bresenham line algorithm. Next is the modifications and improvements. So for modifications we can say that first is the rounding off optimization. Instead of floating point addition we use the simple integer arithmetic. That can be also one good way. One another important approach is anti-aliasing, right. This can be extended to get smooth lines, right, remove the jagged edges which might get, right. Sometimes you might see lines like this, right. So these kind of phenomenon won't occur in case of anti-aliasing. Then generalization works for curves and polygons when extended. So this is a like extension of anti-aliasing, but can be applied across multiple polygons and shapes which we are having. Okay. Now for future scope, I'll say that there is one method called Wu's algorithm for anti-aliased, as I just said, and there are like processes for applying DDA for ellipse and circle as well, right? So the explanation for all these topics which I just discussed, right, the future scope, the modifications, anti-aliasing, generalization, Bresenham line algorithm, right? These are very important. All these are available inside the community. Apart from these, there are additional questions on this same topic as well, right? If you want access to all of those, then I'll suggest joining the Sigma Solver community by clicking the link given in the description below. If you still have any doubts, then feel free to reach out in the comment section below. If you liked this video, then give it a thumbs up and subscribe to my channel for the upcoming videos. Till then, happy solving.
Hey there, before you go, I've got some fantastic content lined up for you. Over here, we've got some videos and playlists you might enjoy. But first, if you haven't already, make sure to hit that subscribe button and ring the notification bell so that you never miss out on any of our future uploads. Thanks for watching, and I'll catch you in the next video.